out, and that means you can roll forward and you can roll backward in the cipher, which is kind of weird, because this gives the opportunity when you have a transaction, you can actually roll back to the earliest beginning, and the earliest beginning of the internal state was the key. So, well, what we then did is we looked better at the cipher, and, well, you notice there some very strange thingy. You notice that it is only connected on the odd bits. And that easily gives a divide and conquer attack. Because, yeah, I'll try it explain it a little bit. It's maybe hard to get it at one time, but you can actually, if you have questions, always come later to me. You generate all the, only 20 bits are used for the filter function, which is a non-linear function, but only 20 bits are used. They are, let's say you take all possibilities for 20 bits, then you shift it 2 times. I mean, let's ignore the other one. So it shifts 1 time, but then you have different bits, so we don't want to know that one. But you shift it 2 times, then you have a new bit, which is announced to this this function, but 1 bit falls off. But you see, 90 bits are the same. So if you have like a range of keystream where you can check on, and you guess like 20 bits, and you shift it 2 times, and you only have like 2 possibilities. Let's say it produces only 1 bit, which is actually the one you want to look for. So that means every time you shift 1 time, you can wipe away half of the extensions by testing on the keystream you already have. Now, if you do this, you only have to do this for, I guess, 21 times, and that means 21 bits, but you have odd and even bits, so let's say 42, but then you have almost a cipher. For like 64 bits, you have the internal state, and that means the key. So, well, another mistake was the statistical bias, which is in cipher. Carsten Knoll already wrote about it, that there is an algebraic attack on it when you use certain bits which are not really as independent or balanced as they should be. Because, well, it should be half times true and half times not true. But if it is like, well, in different values, then you learn from it. And if you have more information, you learn from it quickly. And, well, and this cipher is quite weak, so you don't need much. And the Courtois this year showed a very nice way to exploit a card message, an error message which is produced by the card. I will come to that. That is what I'm going to show, what he is going to have to exploit and what we also exploited. Though his way is quite nice. It's a later publication, but it's very interesting to see what actually happens with if you want to attack a card only. Let's say we forget about all those making traces, getting on a gateway, and having to stand there with your tools. And I mean, let's say you can be busted all the times. But if you just want to in your home suite room and you want to crack your Oyster card, for example, or whatever card, then you can do the following thing. You can authenticate from a certain block. It will send you the random number back. You can, well, say, okay, I have the information. I have my random number, the reader random number in this way, the tag random number, and you encrypt those. Then but of course you don't know that if you are an attacker. So you just send crap, let's say only zeros. The tag sends back his answer if you knew the key, but in this case it was not really the case. So you have an answer reader and an answer tag. I annotated that for some quite some convenience. What you see if you don't have the key, that answer tag will not be the non-stack 2 prime, double prime. It's because it will only react to you. It will only like identify himself as knowing the key if the reader also knows the key. But the strange thing what appears here, if the message you sent, let's say all zeros, has a parity OK, then it's going to check if the nonce you trying to prove that you know the key is okay, and if it was okay, it sends back his identifier. If it is not okay, it sends back an error message and encrypts that one. So that's really weird, because you do not know the key, and he says, yeah, you do not know the key, there's an error, but it encrypts that, which you cannot decrypt because you do not know the key. That's really strange. But it is also a very leaking part of this protocol, because this is happening 1 in 256 times. There are 8 bytes, so you have like 2 to the 8 possibilities there. And this is happening, you can actually exploit it. It's giving away 8 bits of the parity, because the parity was okay, so you can learn from that. And by the way, the error message is 4 bits, so it gives you 12 bits of information about the state by just sending only zeros, crap to a card. So that's really, well, I guess when you do that the right way and you control the random, because that is necessary, you actually have to have a very nice attack, which can work within a minute. Well, if you had, we looked at it, and there was another, I can say, major mistake in it. I want to go back to you to where I first said that after the first nonce is communicated, there is no plain text anymore on the line. It's all encrypted. Well, the thing is, if you know, for example, one sector, one key, then you can authenticate for that one. I mean, this is what happened, and I showed it like 3 times, so this is okay. The card will communicate back to you, and then you both are in a state, and you're going to communicate in an encrypted way. What you're now going to do is you're going to authenticate on a different block where you do not know the key from. So the card will send you a random challenge again. But what is different here? It encrypts that random challenge with a new key you do not know yet. But the randoms are really weak. They are only 16-bit. So you can actually guess that random, and thereby you can actually obtain 32 bits of the key, of the new key. Well, if you already have 32 bits of the new key from a 48-bit key, well, then it's like looking up within a millisecond for the real value you want to have for the other part. So this is actually an attack you can use, because so many cards in the field use a default manufacturer key. They have it on somewhere on the sectors, they use it, and when you invoke that first sector, then you can roll over and into the nested authentication, and you get all the keys out of the others. Well, I'm going to show that in a demo. I hope I have time for that, because, oh, there is something wrong here that you always see. I have here like a card from the Citibank in Peking, which is probably stores some money value, but you can also ride on the metro there and get some lunch from it. Also, I just put it on this very cheap reader. I have very much of them at the RFID village to play with if you want, so come by. What I'm doing now is I'm running the script, and actually it's showing that there's a part missing there. Yes. Okay. So actually it shows that it's trying to look for a default key. Oh, and as you see, it's even on the first block. That's convenient. And then it's trying to calibrate on the randoms. I mean, every computer, if you are using a USB stack between, then you have different timing. So you have to calibrate a little bit on the timings.